Hi there, in this video I'm going to teach you a little bit about similar polygons and how we can solve for missing lengths. First thing I want to show you is what it means for two polygons to be similar. Basically it means they have the same shape but we have different sizes. Now really what that means is this. That's kind of a way to understand what it means for two or more polygons to be similar, but really what it means is this. We have congruent corresponding angles. So all the corresponding angles are congruent. And corresponding sides are not congruent, but they are proportional, which means a ratio is preserved from corresponding side to corresponding side. Okay, so this is what it means for two polygons to be similar. Here's kind of an intuitive understanding, same shape but different size, which means that essentially their angles are congruent and the sides are proportional. Okay, so let's look at an example. Here's an illustration of two similar figures, and what we can do is, those are two similar quadrilaterals, and as an example we'll suppose quadrilateral ABCD is similar. That's a similar sign to, and we're going to match up. So A to B to C to D matches up with E to F to G to H. In order does count. Okay, now since those are similar, note how this diagram does a nice job showing us how corresponding angles are equal. So angle D and angle H are equal, angle A and E are equal, B and F are equal, and C and G are equal. Okay, that has this piece to do with. Okay, but if we want to find the missing side lengths, we know that corresponding sides are proportional, which means this. Okay, the ratio of corresponding side to corresponding sides are preserved. So 5 over 2.5 is the same as 2 to 1, right? And what you'll find is that the ratio of all corresponding sides will be the same, 2 to 1. 6 to 3 is also 2 to 1, right? 7 to 3.5 is also 2 to 1. 4 to 2 is also 2 to 1. Okay, so those are similar, and you can see how those corresponding sides are indeed proportional. They have the same scale factor. So a scale factor, 2 to 1, is what you can use to find missing side lengths. Here's another example here where we have two similar triangles, and what I'm going to do is split them up so you can see them a little bit better. And we'll call that A, B, D. That's this top triangle. And then we'll say that's similar to the whole triangle. Okay, so it's part of this problem that's given. So ACE. And oops, sorry, that should be a D. And top triangle ABD is similar to the whole triangle ACE. Here's ACE. Okay, and after I've separated them, what I'm going to do is label the sides and number the sides. So I got a 12 to 15 to X in this triangle here, triangle ABD. And in my whole triangle, I have 12 plus 4 for side AC, so that's 16. 12 plus 4, and this bottom base CE is 12. And this piece over here I'll call 15 plus Y. Okay, so I want to solve for X and Y. That's what I'm trying to do with this problem. So the first thing I could do is to find what's called our scale factor. What's the ratio that's preserved from side to side? So one way to do that in this problem is to use two side lengths that correspond with one another, which I already know. So 12 to 16 is going to be my ratio that's preserved, right? And I can even simplify that, pull a 4 out of both to get 3 to 4. That's my scale factor. That's my ratio that's preserved, right? So I'm going to kind of keep that in my hip pocket, okay? So 3 to 4, big to small. If I'm trying to solve for X, the ratio of 3 to 4 has got to be the same as X to 12. Those are corresponding side lengths. So 3 to 4, 12 to 16. So AB to AC has to be equal to, because these triangles are similar, BD over CE, right? 3 to 4, 12 to 16 in yellow, equals x over 12 in green. Okay, and that's going to allow me to solve for x. In one of two ways. I can either use the means extreme property for x equals 3 times 12, which is 36, which makes x equal to 9. Or note how to get from a 4 to a 12 you multiply by 3, so you can multiply by this 3 as well. Either way you get 9. So that's my 9 value here. That's the length of BD. And then if I want to solve for y, okay, here are my 15 and 15 plus y. Those two sides correspond. And it has to be equal to the ratio of 15 to 15 plus y, the same scale factor of 3 to 4. All corresponding sides are proportional. So I'm going to set up to solve for y and try to fit this on the same page. So that same 3 to 4 ratio, which must be preserved, which I got from 12 to 16, has also got to be equal to 15 over 15 plus y. Right? So essentially, if I'm following colored patterns, here's my 12 to 16, right? Yellow to yellow, same thing as 3 to 4, equals, right? 15 over 15 plus y, 15 over 15 plus y. Okay? And so now I'm going to undo that because I want to solve for y and figure out what the heck that guy is. So I'm going to use the means extreme, extremely meaningless. 15 times 4 is 60. I have to distribute the 3 there to get 45 plus not y but 3y. When I distribute that 3, subtract 15, divide by 3. Oops, one step ahead of myself. I subtract 45 to get 15, and that gives me my y value of 5. So if y is 5 over here, that makes this whole piece 20. Okay, so the ratio of 3 to 4 is preserved because corresponding side lengths are proportional. So if you'll note 3 to 4, 12 to 16 equals 9 to 12 equals 15 to 20. And that concludes this lesson on similar triangles and really algebraic proportions. Thanks.